we will go over to the next talk with the title Typealike, Near Keyboard Hand Postures for Expanded Laptop Interaction. And this work was published by Nalin, Chhibber, Hemant, Bhaskar, Fabrice, Matulic, and Daniel Vogel.
So good morning, my name is Nalin Chhibber, and today I'm going to present this paper named Typealike, Near Keyboard Hand Postures for Expanded Laptop Interaction. This work was completed at the University of Waterloo with Hemant, Fabrice, and Professor Daniel Vogel. So this research is mostly inspired from the fact that keyboard-based interactions are not just limited to text entry operations. Keyboard also enables shortcuts and hotkeys to trigger frequently used commands. For instance, lining, resizing, and styling of text in a document editor can be performed by pressing known combination of keys or shortcuts. Likewise, it also allows us to switch modes in the applications. For instance, the same mouse drag operation that selects a piece of text in a PDF editor can also be used for panning if the space key is pressed during the operation. So the primary question that we aim to address through this work is how can we expand this input interaction space while supporting the natural keyboard usage? So previous work on this domain is focused on 3 dimensions, on the keyboard interactions, above the keyboard interactions, and interactions while pressing the key. And we specifically focus on previous work, which is conceptually or literally tied to using hand gestures, including static hand postures, hand forms, or hand motions, which are performed on or near a physical keyboard. So for example, on the keyboard interactions such as touch display keyboards, gest keyboard, or flickboard, they mostly focuses on like integrating continuous swiping or pointing like operations into the keyboard. Whereas above the keyboard techniques such as thumb and forefinger interface, air mouse, and space drop enables mid-air gestures for continuous pointing like interactions. And interactions that involve pressing a key, such as finger-aware shortcuts, gest key, and arm and wrist rotations, they focus on overloading key press actions by recognizing how one or more keys were pressed. So this work is different from the previous work in the sense that we specifically focus on discrete commands using static hand postures that are performed on or near the keyboard surface. And we aim for recognizing these interactions without involving a key press. So in Typealike, we explore the idea of using static hand postures that are performed on, below, or beside the keyboard, and that can be recognized using the front camera of the laptop fitted with a mirror reflector. And this gives us like an interaction vocabulary of near keyboard static hand postures that are not just dependent on explicit key press events, and they do not interfere with natural keyboard usage. We also contribute a rich data set of hand posture images captured under different lighting conditions and keyboard patterns. So the Typealike posture set focuses on 3 main design considerations, which are inspired from the base work that involves like recognition of postures without involving a key press, performing the postures on or near the keyboard surface, and postures that are simple and easy to perform. So this gives us 2 hand forms, open and close, 3 wrist rotation angles, 0 degrees, 90 degrees, and 180 degrees that can be performed on 3 different surface locations on the keyboard, below the keyboard, and beside the keyboard. And we can perform this with 2 hands, dominant and non-dominant, resulting in 36 near keyboard hand postures. So we performed 2 experiments. The first one was focused on preference, user preference, and data gathering. So we recruited 30 participants for a lab control study. All participants were aged between 19 to 31 years of age. The average typing speed was found to be 38 words per minute with an error rate of 5.8. And the task was like a game that involved asking participants to perform interactions that involve typing, clicking, pressing a shortcut, or postures. We specifically measured user preferences through a 5-point scale and gathered the hand posture data set through the video that was recorded to the front camera laptop. So participants played a game where they typed a word, clicked a button, pressed a shortcut key, or performed a certain posture. So to generate more samples, we used online data argumentation by asking participants to follow hand movements described in the task during the posture formation. So the result of experiment 1 were quite encouraging. We ended up gathering nearly 350K hand posture images that were captured using different lighting conditions and with different keyboard backgrounds. It was found that postures that involved maximum wrist rotation or 180 degrees wrist rotations was significantly disliked for in terms of comfort and preference. And below the keyboard was the area that was most preferred location for posture formation. So based on the data that we gathered from the first technique, just a second. Based on the data that we gathered from the first technique, we trained a deep convolutional neural network based on ResNet 50 architecture with weights pre-trained on the ImageNet dataset. We used Smith's one-cycle policy to vary the learning rate and achieve faster convergence. Training happened for 10 epochs during that configuration and a batch size of 40. To evaluate the model, we used Monte Carlo cross-validation with 10 random splits. The confusion matrices obtained for each run were aggregated to obtain a final confusion matrix as shown in the figure. So based on this, we ran a second experiment to evaluate the technique where we recruited 20 new participants aged between 23 to 33 years of age. The average typing speed was found to be 46 words per minute with an error rate of 3.5%. The task was similar to experiment 1, where all the participants were asked to type a word, click a button, or press the shortcut key while also performing the hand postures. But this time, when they were performing the postures, the posture was identified in real time by the recognizer, and we were measuring the task completion time and transition time based on that. So for the second experiment, we used the similar game, except this time, it was the postures were recognized when participants were forming the required hand form, and they immediately moved to the next trial after that. So the results of second experiment were evaluated on 2 fronts. The first was task completion time. It was noticed that open hand postures were significantly faster than closed hand postures. Postures that involved 90 degrees of wrist rotations were significantly faster than postures that involved no wrist rotation or maximum wrist rotations. And it was observed that postures that were performed below the keyboard area was significantly faster for hand posture formation compared to beside or on the keyboard areas. In terms of the transition time, it was noticed that postures were significantly faster when participants were transitioning from a typing or clicking reference task. However, when moving back to the reference task, the typing reference task, shortcuts were faster compared to postures. So we demonstrated the use of Typealike postures in several applications for complementary command invocation, mode switching, and game control. For instance, common shortcuts can be invoked by forming an alternative posture to align text in a Word document. We can also use hand postures to switch between drawing and erasing mode during the continuous engagement in graphic editors like Photoshop. Likewise, hand postures can be used to trigger one-shot commands like locking the screen when physically touching the keyboard is not desirable. And finally, we can use hand postures to enable controller-free interactions while playing racing games such as Duck Squad. So overall, this work demonstrates that the use of hand postures is a viable input method to augment existing interactions over the keyboard. And with this, I would like to conclude my presentation, and I'm open to take any questions.
Thank you so much. It's a really great talk and a really great concept. Again, for those who joined virtually, if you have any questions, don't hesitate to paste them into the Zoom chat. And are there any questions? And until the first questions come in, I would like to start with a question. So if I understood it correctly, you're using an RGB approach, right? So what you have over there is a small mirror that films your hands and is able to detect the hand gestures using a deep learning network.
Yes,
right?
we used a monocular camera, like the only web camera that was available. And yes, we were using RGB sensors to detect like hand postures over the laptop.
So my question goes into the direction of the practicability in the real world using the approach, which is by no way exciting, of course. But for example, let's say you're in a very dark environment. I would assume that this approach will not work very well when you're in a very dark environment and your screen is dimmed or you have a dark background and cannot track your hands anymore. Did you think about using like some kind of infrared approach or a depth camera approach to even detect this in, let's say, special circumstances such as lighting conditions?
Right. Yeah, that's a great question actually. And yes, like use of additional sensors, such as like using infrared or 3D sensors would give us better accuracy, and they would probably extend this work to environments such as like very dark, lighting conditions. But in terms of lighting conditions, we only focused on the different shadows that fall when there is adequate lighting on the keyboard surface. But yeah, for very dark environment, yes, it's not possible to detect the hand postures accurately on the keyboard area. And yeah, so using infrared sensors or depth sensors will be like something that can be used as an extension of this work.
Probably when you turn on the brightness of your screen, maybe it's also enough to make this kind of detection. But I think this is something that is really interesting for future work.
Yeah.
All right.
So we did control the brightness during the experiment. So during the first experiment, which was focused on data gathering, there were like multiple blocks in the task, and for each block we set it in such a way that the screen brightness was set to us, like for example for block 1 it was very bright, for block 2 it was a little bit low, and also we used like external lighting like lamps, so that during individual blocks the shadows of hands that fall on either side of the keyboard, they are different for each block. So we did make some changes in the task in the first experiment to make sure that the data that we gather is can be generalized to more common settings. But yes, for absolutely dark conditions where the hands are like very hard to see, it will be difficult to just rely on the RGB camera.
Thank you so much. Are there any other questions? If not, I have a question that I like to ask when I see papers that are using neural networks for making this kind of classification, which is, could you quickly explain how your deep learning architecture looked like and how well you can generalize it from one training set to other training sets?
So like in terms of the deep learning architecture, we use ResNet 50. So ResNet 50 is based on residual networks, and the word 50 comes from the fact that there are 50 like layers in the network. So in terms of generalization, so what we did was, like, of all the samples that we had, of all the training samples, we divided the data set into an 80-20 split, which corresponded to 80% of the training set and 20% of the validation set. And we did this with Monte Carlo cross validation. So we did random splits on the data set and then trained it on 80% of the samples, tested it on 20%, and then we did it 10 times to make sure that the model is equally generalizable for other hands that we will be seeing in the second experiment. So none of the participants in the second experiment were common as in the first experiment, right? So we needed to make sure that the model that we build after the first experiment is well generalized. So after the first study, we like once we evaluated the final performance of the recognizer, we used all the training set to actually train the, like after getting the accuracy of the model, we trained the model on the entire data set and tested it on the participants from experiment 2. And we, like in experiment 2, for example, we had like some experiment logs, and we did not find any misrecognitions during that task, which kind of is interesting. And does that answer your question?
Yes, yes, it does. I'm always only asking how people come up with those architectures for their neural networks for specific use cases, you know? And it seems to me that, of course, you need to adapt it to your actual use case, but sometimes having like a little bit of justification why you have chosen to use a neural network, in this case to solve problems.
Yeah. So we specifically, we specifically used ResNet 50 over other architectures because it was like popular for classifying RGB images, and it could handle many characteristics which were particular to our setting. For example, close up or like partly visible hands or lens distortion, and like different keyboard backgrounds and lighting conditions. So ResNet 50 could handle all these variations, and that's why like it was used as one of the like preferred architectures to build the model.
And this perfectly answered my questions. Thank you again, Nalin. Let's give him another round of applause.